Hi, welcome back. Today we're looking at partial derivatives. Now we talked about how partial derivatives, for example, if I have the partial derivative f with respect to x, this would give me the change of the function in the x direction. And if I have something like fy, that would give me the change of the function in the y direction. But what if we're not traveling in specifically in the x direction or the y direction? What if we're traveling at some sort of angle on the surface? How then do we find the rate of change on that surface? And that's what we'll be taking a look at today. We use something called the directional derivative to calculate this. And how this works is if we have a function or a surface, like if f of xy represents a surface, remember that's just z, and we're sitting at a point on that surface, we can find the directional derivative by using the following theorem. So in other words, here's my surface of mathematics. It's an agoid, and we're standing at some point right there. Now, if I'm looking at the change in the x direction, that's pretty easy. That's just the horizontal. And of course, I also have the vertical change as well, fy, right here. But what if I was facing in at an angle instead? How can I find that rate of change? To do this, we have to first find out the direction we are facing. And we can do that by looking at the following unit vector. U is cosine theta in the I plus sine theta in the j. This is the direction. This gives us the direction we are heading. And we can see this just through the geometry of it. Now remember, this is a unit vector, so it is only length 1. So if I'm looking here in the I direction, this is the cosine of theta, that's in the I direction. And I have my sine of theta, that's my j direction. I can get the direction, or theta, that we are heading. So no longer are we just worried about how much we're changing in the x direction or just the y direction, but now we're going to talk about today how we can find out what the rate of change is in any direction. And here is our theorem. If f is a differentiable function of x and y, then the directional derivative of f in the direction of u is where u is this, cosine theta I plus sine theta j is duff. Now, this is d sub u f of xy, and what this is saying is that this is the rate of change, or the derivative, if you want, the derivative of the function f of xy in the direction of u. Right here. And I'll call it Duff, mainly because I'm a huge Simpsons fan, and I like to say, Duff Man is here. Sorry. Copyright infringement, I probably will get sued for that. So let's take a look at an example. We want to find the directional derivative, Duff, of the function f of xy of the surface at the following point in the direction of u. So this is our u right there. So we're standing on the surface at this point, and we're looking at some direction right here. So when we're looking at some sort of direction, we want to find out, well, what is the rate of change if we're at this surface at this point and we're facing in this direction? Well, let's take a look at our rule. What does it say to do? Duff says to look at the partial of x, cosine theta, plus the partial with respect to y, sine theta. So my rule right away says I have to find my partials. So we're going to do that. Find the partials, fx. The derivative with respect to x is just 2x plus 2. And if I plug in my point there, 1, 1, we would get 4. If I take the partial with respect to y, we would get negative 8y. And if we plug in a point, 1, 1 again, we would just get negative 8. From here, I can get my direction. On the x, we're going to go over 4 units, and then we're going to go down 8 units. And of course, I can find theta, my angle, by taking the inverse tangent of negative 8 over 4, or we get negative 2, and that can give you the direction we are facing. And of course, you can kind of see, if we're on this sort of surface right here, we can already kind of tell what direction we're facing. We're going in, our rate of change is in this direction. So applying our rule now, well, we're looking at u, our direction vector, which is 1/2 I minus root 3 over 2j. Now, this is a unit vector. Very important. You have to make sure they are unit vectors. And you can easily see that if you just find the distance, right? If I take the magnitude, the square root of 1/4 plus the square root of 3 over 4 does become 1. So remember, this is really saying that the sine of theta is 1/2 and the cosine of theta is negative root 3 over 2. And of course, you can use this to get that direction as well as over here. All right, so let's go ahead and find Duffman, the Duff. So we want to get our directional derivative. So we go Duff is equal to, if fx, now remember, it's the cosine of theta, fx times the cosine of theta, which is 1/2. Whoop, I messed up. Sorry, that should be cosine of theta. Messed up, and that's our sine of theta. Sorry about that. So our cosine of theta here is 1/2 plus fy times our sine of theta, which is negative root 3 over 2. Well, we found fx already. That was 4. So we get 4 times 1/2 plus fy we said was negative 8 times negative root 3 over 2. And if we simplify this, we're going to get 2 plus 4 root 3. Now remember, this is a rate of change. It's a slope in that direction. It's our rate of change in our direction 1/2 I plus minus root 3 over 2j. So this is the change, or rate of change, in the z coordinate in the direction of u. Right there. All right. If you go to part 2, we'll take a look at a few more examples. I'll see you then.